So let's consider the following SN2 reaction. First of all, it is a substitution reaction because I am substituting the leaving group by the nucleophile. So what I'm doing here is that I am breaking the sigma bond between the sp3 hybrid carbon and the leaving group. The leaving group can be either a halogen, as we mentioned, or OTS or OMS. The OTS and the OMS are better leaving group than the halogens. So if they are present in place of the halogen, they will speed up the reaction. So here I'm breaking the sigma bond between the sp3 hybrid carbon and the leaving group, and I am replacing the halogen by the nucleophile. So my product in this case is going to be an alkyl nucleophile and the leaving group. So you're going to end up having your leaving group here, which we set the condition for the leaving group, a good leaving group, that it needs to be a weak base so that it can leave easily. For this reaction to undergo an SN2 reaction, the alkyl halide, the reagent, which is the nucleophile, and the solvent, they need to have specific conditions. So we said that the alkyl halide for SN2 reactions needs to be less hindered. Less hindered means that it's accessible because after all, the nucleophile is attacking the R. So the less substituted the R is, meaning the less carbons around it, the better. So here, the sp3 hybrid carbon has hydrogens around it. This works the best. The primary alkyl halide, on the other end, has one carbon and then two hydrogens in there, and then your halogen. So still the nucleophile can easily access this carbon and break the sigma bond. Secondary alkyl halides, they also work, but they are slower than primary and methyl halides. So secondary alkyl halides, so this is the halogen, and this is the secondary carbon, this is the primary carbon. So the nucleophile can come and attack the secondary carbon, but as you can see, the secondary carbon is crowded. It's crowded by the carbons that are connected to it. Although there is room on this side over here for the nucleophile to attack because hydrogen is a smaller atom, but compared to a primary alkyl halide, primary alkyl halides are more accessible to the nucleophile, and methyl halides, they are even more accessible to the nucleophile. So when it comes to preference, always a less hindered alkyl halide works best with SN2 reaction. For the tertiary alkyl halide, so here you go. This is the tertiary alkyl halide. If the nucleophile want to come and attack, the nucleophile will not be able to reach this carbon because this carbon is surrounded by carbons, and those carbons are going to hinder the nucleophile from reaching the sp3 hybrid carbon and breaking the sigma bond and allowing the halogen to leave. So this is why tertiary alkyl halides have no reaction with SN2. That is for the type of the alkyl halide. So SN2 reactions always work with less hindered alkyl halides. It can work with secondary, it's a slow reaction, but cannot work with tertiary. For the nucleophiles, always use a strong nucleophile, which is a negative charge one. And for the solvent, always use a polar aprotic solvent. We said that polar aprotic solvents, these solvents, they do not undergo intermolecular forces, and they will not solvate the nucleophile. So they will not decrease the strength of the nucleophile. The nucleophile will remain strong so that the nucleophile can come, attack the sp3 hybrid carbon, and the halogen leaves. So these are the three conditions. If any one of those are present, then in this case, or any one of those is present, then in this case, the reaction is going to follow the SN2 mechanism. SN2 reaction is a one-step reaction. Nucleophiles are extremely strong. So the nucleophiles will attack the carbon and the halogen is going to leave at the same time to create the products. Because it's a one-step reaction, we can use that one step to determine the rate of the reaction. So the rate of the reaction always depends on the slowest step. But for the SN2, there is no slowest step in here. It's just one step. So the rate of the reaction depends on the reactants of the only step, which is the alkyl halide and the nucleophile. So to put the rate equation for SN2 reactions, the rate in the SN2 is a constant multiplied by the concentration of the reactant, which is the alkyl halide in there. And the alkyl halide is the coefficient of 1 because the reaction is 1-to-1 ratio. And the concentration of the nucleophile. In the reaction, I have the reactants being the nucleophile and the alkyl halide. This is why the rate depends on both of them. So let's say, for example, if the nucleophile increases, then in this case, or the concentration of the nucleophile increases, then the rate is going to increase. If the concentration of the alkyl halide decreases, then the rate is going to decrease. Decreasing the rate means that it's going to be a slow reaction. Increasing the rate, then it's going to be a fast reaction. Let's have an example. Okay, so if you have a reaction like that, the first thing that you would need to check is the reaction in SN2 or in SN1 reaction. So let's start with the alkyl halide that we are using. Our alkyl halide here is a primary alkyl halide. Primary alkyl halides, they work with SN2. So far the reaction is an SN2 reaction. Then I look at my nucleophile here. You need to put your charges. This is an ionic bond between the sodium and the sulfur. So the sodium is going to be a plus charge, and not every time you're going to see sodium. Sometimes I skip the sodium and I show just the SCH2CH3. So you would need to know that sulfur is making one bond, so it is a negative charge. Then definitely there is sodium in there to balance the charge out. So this is going to be my nucleophile. It is strong because it is a negative charge. So this is going to be my strong nucleophile. And acetone is a polar aprotic solvent. So all of these conditions, they satisfy the SN2 reaction. In this case, take a look what's happening. Your nucleophile is substituting the halogen. I still have 3 carbons. So these are my 3 carbons. Nothing is going to change to the 3 carbons. However, the bond between the sp3 hybrid carbon and the bromine. So the bond between the sp3 hybrid carbon and the bromine, this one is going to be broken, and the bromine is going to be replaced by the SCH2CH3. So what I did here is I created a new sigma bond. This is what I did. So that sigma bond here is a new sigma bond. And of course, the bromine left. So when the bromine left, it's going to appear here as a Br minus. I do have sodium in the solution, so sodium is going to come and balance the bromine. There's nothing called a negative charge like that in the solution. If you have a negative charge, then definitely you have a positive counter ion to balance that. So what is the nucleophile in the reaction? The nucleophile is NaSCH2CH3. Precisely, it is this guy over here. It's the sulfur with the negative charge. The sodium is not a nucleophile. The sodium is just a counter ion that is doing an ionic bond with the sulfur. The electrophile in the reaction is the sp3 hybrid carbon. This is what the electrophile in the reaction. So your electrophile here is going to be this carbon. So the electrophile is going to be this carbon over there because of the direction of polarization that the bromine has. So it takes the electrons away from the carbon and makes the carbon partial positive. So your electrophile is going to be the carbon, the sp3 hybrid carbon that is connected to the bromine. What happens when the rate of the uh, SCH2CH3 increases? Well, you need to put the equation of the rate of the reaction. So the rate is equal to the concentration of the reactants because it is a one-step reaction. So it depends on the concentration of the alkyl halide multiplied by the concentration of the nucleophile. So if the concentration of the nucleophile increases, then the rate is going to increase. If the concentration of the alkyl halide decreases by half, so this is your alkyl halide, if the concentration decreases by half, then the rate is going to decrease by half. What happens to the rate when the bromopropane is changed to 2-bromopropane? Now you have a more substituted alkyl halide. Remember what we said, that the alkyl halide should not be hindered. And also we said that SN2 reactions, they do work with secondary alkyl halide. So this one is a secondary alkyl halide, and I'm starting with a primary alkyl halide. So primary alkyl halides are faster than secondary alkyl halides. So where the rate in this case is going to slow down. It's going to be a slower reaction. What happens to the bromopropane? What happens when bromopropane is changed to iodopropane? Well, here, this is my bromopropane, and I'm changing this to iodopropane. So I am actually changing my leaving group in this case. Remember what we said, that leaving a group is better leaving group when it is a weak base. To compare, I minus is a weaker base than a Br minus, then a Cl minus, then an F minus, because I minus is generated from a very strong acid. So this guy over here is going to be the weakest base. If it is the weakest base, implies it is the best leaving a group among all of the halogens. So if I change the bromine into an iodine, it's going to be a faster reaction. And last, what happens to the rate if I change the nucleophile? This is a strong nucleophile. I'm changing that into a weak nucleophile. Weak nucleophile because it is a neutral. This is why it is a weak nucleophile. Weak nucleophiles, they work with SN1 reactions. Strong nucleophiles, they work with SN2 reactions. So if I change that into a weak nucleophile, then immediately the reaction will change and it will be an SN1 reaction. With respect to the stereochemistry of the reaction, it will proceed by inversion in configuration. Let's first consider the mechanism of the reaction and then explain the stereochemistry part. So we start with the primary alkyl halide or a secondary alkyl halide for SN2. We use a strong nucleophile and we use a polar aprotic solvent. As simple as that. And in these types of reactions, you're going to highlight your sp3 hybrid carbon. The sp3 hybrid carbon is going to be your electrophile. This is going to be the E plus in there, and that is the sp3 hybrid carbon. And then you are going to break the bond between the sp3 hybrid carbon and the leaving group. And then you are going to replace the bromine by the nucleophile. The nucleophile here is a strong nucleophile because it is a negative charge, so OH minus is going to come and replace the bromine. All of those are going to happen in one step. So this is what's going to happen over here. Again, I did not add any of the carbons, so my carbons are still the same. I started with 2 carbons on the cyclohexane, and I'm going to end up with 2 carbons on the cyclohexane in there. Br minus is a leaving group, and it's a good leaving group because it is a weak base. Mechanism. So see how am I drawing the mechanism here? When I ask you draw the mechanism, I want you to show the flow of electrons. This means that you would need to show arrows. You would need to show that bonds are forming and bonds are breaking. So always you start your arrow from your nucleophile towards your electrophile. So this guy over here is your electrophile. This is what needs electrons. So you start from the nucleophile to the electrophile. Notice that I ignored the sodium because the sodium in here has no role other than balancing the reaction in there. So it will appear at the end and balance the Br minus. So the lone pairs are going to come and attack the carbon. All of this is going to happen in one step because I'm using a strong nucleophile. So this is going to attack the E plus, and then the bromine is going to leave. Every time I make a bond, I break a bond. This is the rule in there. And I'm gonna end up getting the product. So you're going to end up getting your product. Reaction can also be written in a different format. So instead of the NaOH being before the arrow, I can put it above the arrow. And the solvent, I can put it underneath the arrow. I can also do that. I can put the nucleophile above the arrow. I can put a comma, and I can put the solvent in there. Here you go. So I can do it like that. And both are exactly the same. So from whatever mechanism expressed in here, the reaction happens in one step, and it is a very fast reaction. Let's have another example. If you start with a tertiary alkyl halide and you are using a strong nucleophile and you are using a polar aprotic solvent, well, you won't end up having any reaction because the nucleophile here, which is the OH minus, will not reach the electrophilic site, which is the sp3 hybrid carbon. This is the E plus. And as you can see, that electrophilic site is hindered by all of these carbons. So the OH minus cannot reach this carbon in order to break the bond between the carbon and the leaving group. So the reaction will not happen. It will happen only if the alkyl halide is a methyl halide, primary or a secondary alkyl halide, even though the other conditions are satisfied. Now let's have another example with the stereochemistry. If you are given the stereochemistry of the halogen, then in this case, you would need to show the stereochemistry of the product. So here I'm showing that the halogen is in front. And I know that every tetrahedral carbon has two bonds in plane, one bond in front and the other one is behind. This means that the hydrogen here is going to be behind. This reaction is an SN2 reaction because I'm starting with a secondary alkyl halide. I am having this carbon here, which is the electrophilic carbon, and this is going to be my sp3 hybrid carbon. And the bromine is my nucleophile, and since it is negative in there, this is going to be a strong nucleophile. My solvent is a polar aprotic solvent. So all the conditions here indicate that I have an SN2 reaction. So it is a one-step reaction. Start drawing the mechanism of the reaction. You show your lone pairs of the nucleophile. You start the arrow from the nucleophile towards the electrophile. Now here's the thing. The stereochemistry of the reaction happens here by inversion in configuration, meaning that the nucleophile is going to attack from the opposite side of the leaving group. In order to be able to break the Ci bond, the nucleophile cannot attack from the same side of the iodine. The reason why, because iodine has electrons. So iodine has electrons and the bromine has electrons. If a bromine approaches from the same side as iodine, those two are going to repel each other. So this is why bromine is forced to attack from the opposite side of the carbon that has the iodine. Bromine needs to be in a different plane in this case. So it will attack from behind because iodine is in front, so that it can break the bond between the carbon and the iodine. So the stereochemistry of the reaction now is going to show the product having the bromine behind, and now the hydrogen needs to be in front. So I fix on the bromine and see where the bromine is, and then continue the geometry of the tetrahedral carbon. Every tetrahedral carbon has two bonds in plane, one bond behind and the other one in front, so I know that the hydrogen needs to be in front. The inversion in configuration is in this chiral, is in this center here. So for this chiral center in there, this is a chiral center. It is a chiral center. The reason why, because it does have four different groups around it: the iodine, the hydrogen, all this group here, and all this group there. Okay, so this is a chiral center. If you do the configuration for the chiral center, it's counterclockwise, it is S. Once you do the reaction product, then it's going to be an R configuration. Don't forget that you need to switch here because the hydrogen is in front. Please switch the positions of the hydrogen and the bromine, do the configuration, and then invert it. So when I switch and do the configuration, it's going to be S, and then you invert it and it's going to be R. So your reaction here is going to proceed by always inversion in configuration of your reactant. Let's have another example. Okay. So we are starting here with a secondary alkyl halide. Always check your conditions. The sodium is positive, the CN is negative, so that is going to be, write the Lewis structure for it, please. This is going to be your strong nucleophile, and the solvent is going to be a polar aprotic solvent. So my reaction is going to follow the SN2 reaction. SN2 reaction is one step. So let's go ahead and draw the mechanism of the reaction. So for the mechanism of the reaction, because they are showing you the stereochemistry on the sp3 hybrid carbon, you have to show the stereochemistry of the reaction, meaning that the reaction will proceed by inversion in the configuration. So you're going to start with your alkyl halide. Okay. And you're going to react it with your nucleophile. Since it's an SN2 reaction, then it is a one-step reaction and it is a very fast reaction. I'm neglecting the sodium in here. You don't need to put it. So the nucleophile is going to come and attack from the opposite side of the leaving group. Your leaving group in this case is at the back. So the nucleophile is going to come and attack from the front so that the leaving group can easily leave. Pay attention that your leaving group has lone pairs on it. And as we explained earlier, that your nucleophile cannot attack from the same side as the leaving group because these two are going to repel each other. So whenever you want to draw the arrow, if you are drawing the arrow and having your nucleophile like this attacking from the same side or the same plane as your leaving group here, those are going to repel each other. So in this case, your arrow position is going to be wrong. Make sure that the cyanide attacks as far as possible from the leaving group. Pay attention to your owl drawings whenever you are drawing these reactions. So when this happens here, I need to show that the cyanide is going to attack from the front because the bromine is going to be kicked out from the back. So my product is going to be, I'm going to end up having my hydrogen, and the cyanide is going to be on this side. So you're going to have your cyanide, which is in front. This makes the hydrogen to be at the back, plus of course the bromine which is a negative charge that is going to be balanced by the sodium. You can skip the sodium or you can write it. It is not a big deal. We need to find the configuration for both chiral centers in there. For SN2, the reaction proceeds by inversion in configuration. So if this chiral center is an R, then this one's going to be an S, and vice versa. So let's figure out the configuration of this chiral center. So you have your carbon. On the carbon, I do have a group number 1, and then I have group number 2. This is a group number 3 priority, and 4 is in front. So I need to switch here. But let's first write them as is. So 4 is in front. You have 3, and then you have 2. Both 3 and 2 are in plane. We're going to go ahead and switch both so that the hydrogen now is behind, and the first group, which is the bromine, is in front, and then I'm going to keep the 3 and the 2. And then do the configuration, and this is going to be 1, 1, 2, and 3, and this is going to be an R configuration. But this configuration that I did is for the switched one, not for the original one. So this is why I would need to invert that. And my true configuration now for my structure is going to be an S configuration. So this guy over here is going to be an S configuration. Let's do the configuration for this one. Already hydrogen is behind, so I don't need to switch the groups. So this is going to be priority number 4. Priority number 1, priority number 2, and priority number 3. And I'm going by 1, 2, and 3, and this is an R configuration for the chiral center. As you can see, I am proceeding by inversion in configuration. Another example over here, I'm starting with a primary allylic leaving group. I switched my leaving group from a halogen to OMS, so my speed of the reaction here is going to increase. Primary allylic leaving groups, they are as stable as secondary leaving groups. So this reaction over here can proceed with SN2 reaction. I am having my nucleophile here. Let's put the charges. This is lithium, which is positive. We have an ionic bond in here. And this is the carbon with a negative charge. So this guy over here, since it's negative, it's going to be our strong nucleophile. Please put your charges, especially whenever you have a metal next to the negative element. I don't have a chiral center, so I don't care about stereochemistry of the reaction. All I care about is to show that my nucleophile here is going to come, and it's going to come and attack the carbon. Since I don't have a chiral center here, this is not a chiral center, so I don't need to show that my nucleophile is attacking from behind of the OMS or from the opposite plane of the OMS. It doesn't matter because this is not a chiral center. So the nucleophile is going to come and attack the sp3 hybrid carbon. This is the electrophile in this case. So it's attacking the E+, this is the partial positive, and the OMS is going to leave. It's a one-step reaction, so just to create your new bond in there, and what you added is the CH3, just put the CH3. The OMS is the leaving group, and that is going to be balanced by the lithium. Whenever you see that you have a chiral center, so here I do have a chiral center, so if the chiral center is shown, then you have to show stereochemistry, and you have to show that the reaction proceeds by inversion in configuration, meaning that if you are starting with an S chiral center, then your product is going to be an R. This is what inversion means. So here I'm starting with a primary alkyl leaving a group. It is a primary because the OTS is connected to a carbon, and this carbon is connected only to one carbon. Neglect the D. D is a deuterium, which is the isotope of a hydrogen. So the cyanide now needs to attack from the opposite side of the OTS. Now notice that your leaving group is not in front or behind. Your leaving group is in plane and it is to the right. So whenever you want to draw your product, the cyanide is going to be to the left. So this is why I did invert everything in there and put the cyanide on the left. And then do the configuration, and then you're going to end up getting the R. This is another example. Your leaving group is in front, then the product or the nucleophile is going to attack from the back. Again, when your leaving group is in plane, then you have to rotate the whole thing and make your nucleophile be in plane, but it needs to be on the opposite side. So if you're starting with your leaving group to be on the right, your nucleophile is going to be on the left, but it's going to stay in plane. Here, if it is in front, then your nucleophile is going to attack from the back, and vice versa over here. It's going to proceed by inversion in configuration. SN2 is one step. And normally when we draw these reactions, we draw their energy diagram. The energy diagram is the sum of the reaction. So what's happening? It explains what's happening in the reaction. It explains how bonds are formed and how bonds are broken. So it shows your reactants and it shows the products in there. It's a plot of the energy of the reaction versus the time that the reaction needs in order to go from the reactants to the products. This we call it, it's the x-axis, and we call it the reaction coordinates. So we start with the reactants. The reactants are going to be low in energy. And here's my reactants in there. And the first step is that the nucleophile is going to come, attack the R, and the halogen is going to leave. So you're going to end up having a transition state. This is going to be your, this is the peak of the reaction, is the transition state. And the transition state shows that bonds are forming between the nucleophile and the electrophilic site. This is the R. And bonds are breaking between the electrophilic site and the halogen. This is the transition state. To represent the transition state, which is the TS, you represent it like this, and every bond breaking and bond forming, we represent it as a dotted line, and everything needs to be in brackets there. Whenever you draw the transition state, then you're going to go straight to the product. The product should have a low energy or a lower energy than that of the reactants, because the reaction here needs to be an exothermic reaction, meaning that the change in energy between the reactants and the products need to be negative. So delta H is exothermic, delta H is going to be negative. Products need to be always lower in energy than that of the reactants for the reaction to proceed towards the products, for it to be favorable reaction. For the activation energy determines how fast the reaction is. And you always want your activation energy to be small so that your reaction is fast and not slow. So in order to know, you need to compare two reactions together to know their activation energies. The one that has a smaller activation energy is going to be a faster reaction. So here the activation energy is measured from the reactants to the transition state. There are more reactions in the practice problems that are posted on eCampus. Please practice those for the SN2 reaction.